All right, we're going to continue on this topic of evaluating limits algebraically. And the two trig function limits theorems, if you will, are the limit as x approaches 0 of sine x over x, and we're going to figure out what that is. And then from this, right, we're going to figure out what the limit as x approaches 0 of cosine x minus 1 over x is. Okay, so these are two commonly used limit theorems in calculus, and you kind of just have to know them. And I just, want to caution you that, what we're going to do today in evaluating limits algebraically of these trig functions, it's a little bit tedious. You can still do it, right? You just arrive at the answer using these theorems. But once you're in calculus, there's actually some rule called the L'Hopital's rule that makes things a little bit easier. Okay, but for now, we're just going to kind of grind it out. All right, so you already know there's three ways to evaluate limits, right? You can evaluate algebraically, graphically, or tabularly. And you can always use direct substitution, right? If you plug in 0 over here, sine of 0 is just 0. And if you plug in 0 in the denominator over, you're also going to get 0. What I forgot to mention, right, is when you have 0 over 0 in the previous video, it's called indeterminate form. And usually what that tells you is that you're going to have to manipulate this. It doesn't mean the answer is undefined or does not exist, or even you don't even write indeterminate form. It just means that there is some kind of answer that this limit of this function actually goes to, right? And so over here, I already graphed it out for you. I don't expect you to know this by hand, right? This is what the this is what the graph of sine x over x looks like. And if we use a graphical approach, right, as x approaches 0 from the left, it looks like it's f of x is going to approach 1. X approaches 0 from the right, f of x is also going to approach 1. So just graphically, you can see that the limit of sine x over x is equal to, limit as x approaches 0 of sine x over x is just equal to 1. Okay, so that's just something you have to memorize. It'll be useful in the beginning of Calculus AB next year in semester 1. Okay, now that we know that the limit as x approaches 0, sine x over x is equal to 1, we can kind of figure out what this limit is, right? Just by performing algebra here. But before we do that, so always try direct substitution, right? If you plug in 0, cosine of 0 is 1. And then if you plug in 0 over here, right, you're going to get indeterminate form again. IDT form. I'm just going to abbreviate. And again, what that tells you is that you're not going to be able to use direct substitution, but there is going to be an actual answer to this problem. Okay, so instead of doing this graphically, right, I could use this, my graphing calculator, or go to Desmos. I'm going to apply some techniques that we've already learned in the previous videos. Is that, remember, the x is actually inside the argument, so don't get confused. Don't say x minus 1 is in the argument. I'm going to multiply by the conjugate of cosine x minus 1, which is cosine x plus 1. Okay, so multiplying this by the conjugate, I'm going to get cosine squared x minus 1. And I'm not going to quite FOIL just yet. And by the way, right, as you guys are doing these limit problems, keep writing the limit as x approaches 0 until the very end when you plug in. All right, so right now, even if you plug in 0, right, cosine of 0, which is 1, 1 squared is still 1. You're still going to get 0 in the numerator, and then you're going to get 0 in the denominator. So it's not going to quite work just yet, right? But we're going to manipulate, right? Cosine squared, we know, is just 1 minus sine squared x. And if you plug in 1 minus sine squared x, right, these 1's are going to cancel out, and you're left with a negative sine squared x. Okay, so that's just using a trig Pythagorean identity substitution. All right, well, again, you're still going to, if you plug in 0, right, just kind of plug in 0 along the way, see if it works out, and it doesn't, right, because sine of 0 is still 0. But now that we know the limit of sine of x over x as x approaches 0 is equal to 1, we can actually manipulate this by rewriting this as the limit as x approaches 0 of negative sine x over x times sine x over cosine of x plus 1. Actually, what I'm going to do is I'm going to move the negative over here. Okay, so convince yourself this is the same as this, right? Okay, now you're going to use a limit property. It's on page 755 in your textbook. There's, I believe, 5 properties. You're going to use the product rule, okay? And what the product rule basically states is that the limit of the product is the product of the limits, meaning you can kind of take the limit of this product, or sorry, limit of this factor and limit of this factor individually, okay? So the limit as x approaches 0 of sine x over x, again, it's on page 755 of your textbook, times the limit as x approaches 0 of negative sine x over cosine of x plus 1. Okay, and actually this technique that I'm splitting up a squared function as sine x times sine x, it's going to be used in your homework. Okay, so it's useful to kind of understand where this comes from. Okay, well, we already know the answer to this, right? The limit as x approaches 0, sine x over x is just 1. This one, you can actually use direct substitution, right? Because if I plug in 0 over here, sine of 0 is 0, cosine of 0 is 1, right? And I'm not going to get a 0 in the denominator. 1 plus 1 is 2. I mean, there's no such thing as a negative 0. You can write the negative if you want, right? But 1 times 0, we just know, is 0. And so the limit as x approaches 0 of cosine x minus 1 over x is 0. You can use that information or theorem, if you will, in your homework. Okay? So this one I showed you graphically. And after I showed you, after we arrived at this graphically, we can manipulate based on our knowledge of, multiplying by conjugates and whatnot. And then we also went over some limit properties. Again, this is on page 755 in your textbook. The limit properties. I would go back and review those rules. Okay, it's called the product rule. All right, so now that you have these two theorems, we're going to use any one of these two theorems in doing the examples. Okay, so let's take a look at this first one here. The limit as x approaches 0 is sine of 2x over 5x. And the goal right here is to use one of our theorems to see if we can manipulate this, right? Again, if you just kind of do it in your head, right, by direct substitution, always do that first step of direct substitution. Sine of 0 is 0. Plug in 0 over here. 5 times 0, of course, is 0. So 0 over 0 is indeterminate form. Again, doesn't mean there's no answer. Doesn't mean it's undefined. Doesn't mean the answer is 0. It just means you're going to have to manipulate somehow. And the way I'm going to manipulate, right, is I'm going to multiply top and bottom by 2 over 2. And you'll see why in a minute here. If I multiply top and bottom by 2 over 2, actually I'm going to run out of space downwards. I'm going to write horizontally. Again, write the limit as x approaches 0 of sine of 2x. And what I'm going to do right now, right, this is 5 times x times 2. I'm going to put this 2 over here. I'm going to put this 5 over there. All right, so what you have right now is 2/5. All right, now, this value right here, right, looks very, very similar to this. And what you can do is just do a quick substitution. You could say let theta is equal to 2x, right? And so if I substitute right here, sine of theta over theta, right? Now, your limit in this argument down here changes. Make sure you change this limit symbol as well, okay? So as x approaches 0, right, if theta is equal to 2x, if x approaches 0, right, basically you plug in 0 here. Theta is also going to approach 0. And over here, you just have a constant, okay? So in your product rule, or sorry, in your properties of limits, this constant can just come outside, but you could just leave it here for now, right? And if I ask you what is this, you would just say that's 1. 1 times 2/5, of course, is 2/5. And that's how you would show your work on this particular problem. Okay, so on a multiple choice, exam, right, you can just see that basically it's just going to be 2/5. But this is how you would show your work. All right, so moving on to this next example. Cosine of 3x minus 1. Sorry, I was reaching for a pencil. Cosine of 3x minus 1 over x. On this particular problem, right, only the 3x is inside the argument. Okay, so if you're not quite sure, you're always welcome to email me what's inside the argument, what's not. All right, so this is going to be suspiciously, it's going to look something very similar to the second term that we had with the cosine, right? But right now there's an argument of 3x inside the cosine. And so just like the previous problem, right, what I'm going to do is multiply by 3 over 3. And again, writing it out horizontally because I'm running out of space. You're going to have cosine of 3x minus 1 over 3x, right, times 3 over 1, okay? All right, now, you can use a theta substitution, right, because as theta is equal to 3x, and as x approaches 0, right, as x goes to 0, this theta right here, right, if x goes to 0, theta is also going to go to 0. And so you can use your second theorem here. Right, we already know the answer to this limit is just going to go to 0. And 0 times 3 is just 0. Okay, so really you're just manipulating using those trig functions theorems that we learned. All right, moving on to number 5, right? This looks kind of weird because now the limit is going to -3, but you'll see in a second that once we use the direct substitution, it's basically the same concept. So let's take a look here. What I would do right now is just factor. So in my denominator, I'm going to have a GCF of x squared that I can pull out. And this looks very, very suspicious, right? Sine of x plus 3 over x plus 3 looks something very, very similar to what we can use on theorem number 1, right? Limit as x approaches 0, sine x over x is equal to 1. But this one, this x right here is approaching -3, not 0, right? And that's where your theta substitution is going to be helpful. But before we do that, let me use my limit product rule. Okay, so again, this is the product rule of limits. The limit of the product is the product of the limits. So as x approaches -3, a sine of x plus 3 over x plus 3 times the limit as x approaches -3 of 1 over x squared. Okay, so just pause that for a minute and see if that makes sense, right? Basically, this is a product of sine of x plus 3 over x plus 3 times 1 over x squared. I split it up as a product, and I just took the limits of each individual factor, if you will. Okay, it's called the product rule of limits. It's rule number 3 on page 755 in your textbook. All right, now, this one we can evaluate, right? The limit as x approaches -3, well, of 1 over x squared, that's just 1/9. And this guy right here, this almost looks like your theorem, right? But you'll see that it actually is. The only thing that I have a little reservation is that why is this going to -3 as opposed to 0? Well, again, do a theta substitution, right? If theta is equal to x plus 3, as x goes to -3, right, theta is going to approach 0, right? If you plug a -3 over here, theta is actually going to go to 0. And so this becomes the limit as theta goes to 0 of sine of theta over theta, right? Remember, theta is just x plus 3. And now if I ask you, what is this value? You would just say, well, that value is just 1, right? And your final answer is just 1/9. Okay, so nothing to it. If you do a substitution, use the product rule of your limits and try to get it look like this ultimately. And then you can say, well, this just equals 1. And then this one, I just use direct substitution. Okay. Again, in the beginning of the video, I should have done the plugging in the -3, right? -3 plus 3 is 0. Sine of 0 is 0. And if you plug in -3 over here, it's also going to make your denominator 0. So you will have the indeterminate form. Okay, so always try direct substitution first and see if you can get any easy answer. All right, so this last example on tangent is quite similar, right? You're just going to have to use your reciprocal or quotient identities for tangent, right? We don't have a theorem for tangent, but you already know tangent can be rewritten as sine of 3x over the cosine of 3x, right? That's your tangent of 4x, or tangent of 3x, I should say. You still have the 1 over 4x over here, so don't neglect that. All right, so really for this type of problem, what you just need to do is manipulate, rearrange terms, right? Remember, this is just a product of 4x times cosine of 3x. You can always switch it, right? Multiplication is commutative. The order which you multiply does not matter. So let's keep manipulating here. The limit as x approaches 0 of sine of 3x times 4x times 1 over cosine of 3x. Okay, now just like the previous examples, right, I need to make this kind of look like sine of 3x over 3x. And the way to make it look like 3x over 3x is multiply top and bottom by 3 over 3. Okay, and I'm going to move this 4 out here. Actually, I'm going to move my 4. This 1/4 right here is just a constant. You can move the constant out in front. Okay, so I'm going to move the constant out in front. This is your constant rule for limits. If you don't know what that is, it's on page 755. It's called a scalar multiple rule, but basically the constant can just come out. Okay. All right, so multiply top and bottom by 3 over 3. Okay, so now that you can see that I'm going to have 3x, sine of 3x over 3x, right, you could use your theta substitution again. And what you can do with this 3 right here is just move it out, okay? So I'm not going to expend an extra line over here. I'm just showing you that I'm multiplying this guy by 3 over 3. So I'm going to change this 1 into a 3 because, remember, the constant can come out in a limit. So let me just erase that 3 right here. Okay, so use your theta substitution again. 3 over 4, the limit as theta goes to 0 of sine of theta, right? This is 3x now, right? Sine of 3x over 3x. So theta is equal to 3x. And over here, right, I'm going to use the limit product rule, right? The limit of the product is the product of the limits times the limit as x approaches 0 of, I guess you can keep this in terms of x still, or you can keep it in terms of theta. It's up to you, okay? So if you want to keep it in terms of theta, you can say the limit as theta goes to 0. So let's do that, actually, because we already said this is 1 over cosine of theta. Right? And this guy right here is just going to go to 1, right? This guy right here, if you plug in theta, right, is 0. Cosine 0 is 1. So 3/4 times 1 times 1 is just 3/4. Okay, so a lot of substitution going on. Some limit properties, like I said, you're like, how did you get this? How do you split it up? It's page 755 in your textbook. Why did the 3/4 come out? Again, the limit constant, or I guess your textbook calls it the scalar multiple rule. It's rule number 1. And again, a lot of algebraic manipulation, moving the terms around. Okay.